Hey, welcome back to Introduction to Computer Networks at NTU. All right, and this is Polly again. So again, let's go over the announcements. Okay, so let's go straight to the assignments that will be due this week. Yeah, guys, you guys, yeah, some of you had some trouble doing PA1, but I can tell that you guys have no trouble eventually finishing PA1. And this week we'll move on to PA2. I in fact see some of you have already completed PA2. Okay, good for you. In fact, guys, all 9 PAs, all the setups are done. And all the necessary files for the PAs are in already your account. So if just find that it's so interesting, the PAs, you couldn't stop. You can actually go on. And one can actually complete all the way to PA9, okay, if you want. All right. Other than PA2, we have 2 quizzes and potentially a third one. Chances though, but let's see how we go. Okay, so we have quiz 6 and 7, potentially 8 due this Saturday. Now, something I want to add is this, okay? The first 2 weeks at NTU will always be hectic. Okay, so some of you are looking and waiting for the echo, you're not sure. So you're not quite sure whether you should start working on the assignments. And some of you, especially for this course, I'm sorry about that, it's a little bit inconvenient. We are not on NTU Cool, and the course is online. Okay, and Polly is just using a assortment of tools available online and see if I can teach online with the minimum cost as well. Okay, so it's a little bit hard to find, and a couple students eventually discover where we are, but it's really late, and they are already registered and lucky getting into the class before the class start. Okay, now for these couple reasons, we'll overlook the late assignment policy for week 1 and 2's assignments. Okay, that means the week 1 and week 2 assignments, the official due days, are this Saturday, 6 p.m. So guys, if you are late getting the echo or late discovering where the courses are, where the assignments are, you still need to turn them in, except that it's okay. You can work on them by the end of the course. Okay? By the end of the week. And now, let's start. Okay. If you recall, oh, by the way, guys, I would really like to be able to greet all of you. Okay, so I think I went all the way to Katie, which is all the way up here. All right. So, hey, guys, we don't have all that much time. So maybe what we can do is that I start doing the greeting a little bit earlier, start the stream a little bit earlier. Then I can greet all of you before the class actually start from tomorrow. Okay, we'll try that and see. So come a little bit earlier, okay, so Polly can see you guys interacting with me. And so for today, okay, let's cut the greetings and come back to the subjects, okay, that are a little bit more important here. So last week, we finally started talking about the core of a network, right? There are 2 design principles, one called circuit switching, and I kind of just say CS, okay, that indicates circuit switching, and PS will be packet switching, okay. So the last couple of videos are more about packet switching, as this is the principle that the internet is designed on. So in those couple of videos, you see that in a packet switch network, we are no longer streaming bits, okay, over a circuit. We cut the data into packets, okay. We send 1 packet at a time, okay. But how big the packet should be, right? So obviously we don't want to send a big file. You see from a numerical example that it's not a good thing. It's not good to send big files, but Polly also talk about it, right? During the video, in between the videos, that 2 small packets are not good because there are these control bits in a packet. If the number of bits for serious data in proportion is lower than the control bit, it's not an efficient way of using the bandwidth either. Okay, so you want the packet that is somewhere in the middle, but exactly what size it should be, it really depends on the network. Okay, it depends on the throughput as well. But if you will have opportunities to observe on the internet, okay, for serious data packets, you will see the sizes very often 1400, 1600 bytes. Okay, I am not sure why, but it seems that, okay, empirically, okay, the designers of all sorts of protocols discover that that seems to be a better size to send. Okay. Now, in the very last video, Polly spent more time talking about this store and forward characteristic of a packet switch network. Okay, so essentially on the internet, a packet, upon arriving at the router, we store all the bits on the packet first before we forward the packet further. Okay, why? There is a very important information on the packet called the destination address. A router actually needs to see that first before a router decides which way to forward the packet further. If you recall, one characteristic of the core of the internet is that every router oftentimes have multiple connections to the rest of the world, to the rest of the internet. And so you have multiple choices. Okay, as a router, it has multiple choices, and to decide, it actually look at the packet. Inside there's this destination, and that is how the router decides which way to forward the packet. Therefore, a packet must be stored before it gets forwarded. But a packet can potentially be stored, okay, at a minimum portion of a packet and forwarded a little bit further. Okay, if we can do that, the performance will be closer to circuit switching. Okay, so the delay can potentially be shorter. And you know what? On the internet, in a packet switch network, we do have this flexibility. We talk about it. One can simulate the behavior of a circuit switch network on a packet switch network. And that thing is called virtual circuit, and that is what this next video is about. It's about 3 minutes. Okay, so let's see. The next few slides, they are still somewhat important. Sorry, misclick on my Stream Deck. It's this video, sorry. And actually, in a packet switch network such as internet, we can potentially emulate a circuit-like behavior that is called virtual circuit network. So instead of looking at the destination field in the packet header, we look at a very special header field called the virtual circuit ID field. Okay, so there's a tag there, carries a number. Okay, that number determines which is the next hop. So inside a packet, there could be many fields in the packet header. One is called destination. There's another one called the virtual circuit ID, and one can look up that field and decide which is the next hop. And how do we do that? We'll talk about that also in chapter 4 and in chapter 5. And what's nice about this approach is that we can then try to ensure, okay, all the packets for that stream traverse a fixed path. In a way, packet number 1, 2, 3, 4, chances high that they arrive in order. In this case, in case routes might change, if the later route is shorter than the earlier route, chances there packet 1 might arrive after packet 2. So, packet switch network. To sum everything up, this is general communication network. 2 different flavors depending on which philosophy we design the core of the network. If we are going for a circuit core, it's called circuit switch network. If we are going for a packet-centric core, packet switch network. In circuit switch network, we know there are different ways of dividing resources into pieces. Frequency division or time division. But either way, it's very regular following certain order. Things will need to be reserved. There's a call setup delay. It's good for long-lasting calls where you will prefer data not experiencing variation in delay, not experiencing losses. But this is very resource consuming. Each time we will not be able to allow many users going on at the same time. On the other hand, packet switch network, simpler, flexible, no idle resource, but we might have congestion. So that's this track, datagram network. We look to the destination network address and then decide which is the next hop to forward. And so we need to store the entire packet, and so they might get queued and they might get dropped in case there's not enough space in the queue. But we can also try to emulate a circuit behavior using the virtual circuit tech, which allow us to look up into the packet header field that's a little bit faster and streamline the process more or less and maintain packet arrive orders. Packet switching versus circuit switching. All right. Next is just the final bit of the core. And this is to show you how the core of the internet look like. Okay. And so Polly is going to show you 2 videos, and that takes you through the history of how the internet evolved to be a huge one nowadays. Okay. So the first video, there are also 2 parts. At the beginning, you will see that as an academic project, okay, the design of the internet at the beginning has some reasonable engineering sense in it, okay. But as the internet go a little bit more public and there are real users, okay, coming in using the internet, then the design of the internet is actually adapting to the actual user demand, okay. So 2 phases, okay, in the first video, and this one almost 5 minutes. Internet structure. It's a network of networks. Earlier we learned we have end systems at the edge of the internet. They're connected to the core through the access networks, which are part of these access ISPs. Now, some of these ISPs serve home users more. They're called the residential ISPs. Others serve companies and universities. They are more often being called institutions and ISPs. Well, either way, any 2 hosts in these ISPs wanting to send packets to each other, their access ISPs will need to be interconnected. As a result, we see a network of access networks. Over time, they grow pretty large and complex. And much of these growth is driven by the economics, and some of it driven by governmental or business policies. In the next few slides, what you'll be seeing is essentially the evolution of the internet. What I'm drawing here is a bunch of these access ISPs, or I call access nets here on this figure. Let me just omit drawing the end systems because there's just going to be too much of them and the picture gets too messy. So the first thing the internet engineers are thinking is this: how are we going to interconnect these guys? Well, one obvious way is, how about connecting them all? But as a result, you see there are n square connections. And when the internet grows, adding one more access net, we'll need to add n extra links. So this is going to be a very expensive thing to maintain. And so internet engineers go with the other extreme. Everyone connects to one global ISP in the middle. So data come here, and the global ISP transits the data for the access net to the destination. Similarly, here. So in a way, the global ISP in the middle here is providing transit services to the access nets, which are the customers. Now, as the internet grows, as the number of these access nets grow, then there will be more paying for the transit services. Gradually, the global ISP will begin to see profit. And when business is profitable, you see competitors. So now we have not just one global ISP, but multiple global ISPs. So A, B, C here are 3 global ISPs. They're competitors, but unfortunately, they also need to collaborate. Because what? Just like the access nets needs to be interconnected so that they can serve the end systems, their customers. ISP ABC will also need to interconnect so that they serve their customers, the access nets. All right, so must interconnect. There are two ways for the global ISPs to interconnect. First is to establish peering links among each other. The other is to connect through these IXPs, Internet Exchange Points. Now, these IXPs are special. They're typically set up by government fund or by the nonprofit organizations because it's kind of important that we have these, third company there maintaining the basic operation of the internet to avoid companies, commercial companies, to dominate. So that's pretty much the structure of the internet for a long time. But over time, we see more. So local communities such as this guy and this guy here can also grow. When there's enough number of these access nets around, we begin to see regional ISPs showed up. What these regional ISP is doing is this, offering lower price internet access to the access nets and try to negotiate internet access with the global ISP with a lower price. So hopefully the regional net here finds a margin of profit. So profit here and saving money here. For global ISP, this might not be a bad thing at all because it only needs to deal with one customer, which is the regional ISP, instead of multiple of them. Okay, so less overhead. All right, so now you see that there are these big ISPs. Okay, that's where how the core internets are structured. Okay, at the center, at the very center, are these very high tier ISPs. And then there are these occasionally IXPs, and sometimes there are these second tier, third tier ISPs. Okay, but in more recent years, we have this thing. So ISPs are internet service provider. Nowadays, we have the content service providers. Okay, now that the ISP are usually the companies that actually bury cables all around the city so that you can connect to the routers. Okay, and ISPs are more often also the companies hosting many routers, providing connectivities from one city to another city, and from one nation to another nation. But the content service providers are different. Okay, content service providers are more providing content. Okay, therefore they are called the content service providers. So who are these content provider companies? For example, Google. For example, Netflix. Okay, because they have all kinds of servers around for us to connect to. For example, to get access our emails. For example, to access videos, hot videos. Okay, so they provide content. Okay, but these content providers nowadays are huge, so that they are very well connected. They are also everywhere globally. So they are also everywhere, okay, as big as these ISPs, okay, even though these content provider networks do not sort of set up cables, they do not connect themselves, provide connectivities from one nation to another, but they are huge, okay, and with these content provider networks in place, the look of the internet, okay, gets a little bit strange. And this structure has been there for a long time until about a decade ago. Content provider networks showed up. Let me talk about content provider network by example. So let me use Google here. It'll be easier for you to understand. So Google established these data centers worldwide. Okay. What they do is to go to access networks locally where the data centers are, and then ask to connect to the access network, their data center. Now, the number of machines they are maintaining there at their data center and the connections they are buying from the local ISP are actually comparable to the global ISP here. The entire infrastructure there at the content provider network is just as big as the global ISPs in the middle. But what's a bit odd is this. the content provider networks, they're actually physically at the lower level of the hierarchy. As opposed to the global ISPs, they're at the center of the hierarchy. Scale comparable, but where they are in the hierarchy, very different. All right. In the next picture, let me try to draw the network slightly differently so that you see where they are in terms of how resourceful these provider networks are. You see here then, the most resourceful one at the top, the least resourceful one at the bottom. So at the center, we have Tier 1 ISP and content provider network. Tier 1 ISP interconnect to each other through peering link, and they also connect to the IXPs. Content provider network somewhat different. They connect to the local access ISPs and IXP. All right. But keep in mind, this is not exactly absolute. Some Tier 1 ISPs might also have access ISPs connections. Google here, if this Tier 1 ISP offers a fair price, might also establish a connection. All right. Good. Now, the final slide is just to give you a rough idea what's inside a Tier 1 ISP. As I'm drawing here, it looks simple, but it's actually quite complicated. This is Sprint's backbone. Sprint is one of the major operators in the US. It's also a Tier 1 ISP. Each of these red dots is called a POP, point of presence. So the role there is pretty much like a data center in Google. It's a rack of machines. In this case, a rack of routers. Okay, so rack of these routers. They're interconnected between each other, and they're also offering connections to the customers. And some of them might be connected to other Tier 1 ISPs. And these links are to go further up into the backbone, in the hierarchy of the backbone in Sprint's network. And this is internet structure, a network of networks. All right, so that was essentially the look of the internet core. Yeah, so during the past two videos, I see that many of you provided feedback saying that the volume of these videos are lower. Yeah, in fact, these are the two videos where the volume are the lowest. Okay, because these two are also the oldest videos Polly has recorded, and it was done like 6 years ago. So guys, but the previous students have not mentioned the issue, but I guess I would try to process the video such that I can raise the energy of the audio part of that video. Okay, so that's very helpful. Second thing is if we go to Discord, okay, we see students asking questions on Discord. So these two questions are about the videos we just played. Okay, is there a most efficient way to build a global ISP or otherwise? Can the most efficient be defined? This is a very good question, Ivan. It really depends on the physical location of the ISP and how big this ISP is. Okay, so some ISP might focus on covering a particular region of users. Okay, and some ISPs can be huge, can be nationwide. Then that company might have a Tier 1 ISP network here, and almost everywhere. Okay, so it really depends on the ISP. Okay, and you also mentioned this notion, a global ISP. Okay, so that I have not seen one yet. Okay, a very typical situation is that within a nation, okay, within one economic region, okay, because sometimes in Europe you will see a company that's large enough that covers services from multiple countries nearby. Okay, but in one economic regions, and for some reason, mostly in proximity, then you see a ISP. Okay, so I have not yet seen a global ISP, typically because of the geographical diversity, okay, we have in this world. Okay, if you are talking about what is the best architecture for the global internet, okay, it will be a super interesting question. I don't know. Maybe there is. Okay, but Ivan, as you can see in these two videos, internet is changing. Okay, and it's expanding. Nowadays, the core of the internet is still expanding because the geographical reach is still spreading. Okay, and very often that at the core of an ISP, okay, inside the ISP circle or cloud like that, it's also expanding in a way that there are more routers and there could be higher level of hierarchy, more levels of hierarchy. And really depends on how the business expand. I would say that maybe at a given time, there's a more efficient way of doing it. Typically, a lower level of hierarchy will be better because the number of routers a packet will traverse is smaller. As you can see, internet is store forward network. The lower number of hops you transfer the packets will be better from the user sense. Okay, but it will be harder for the ISPs to manage a large network as well, because it will be easier if you set up a smaller network for different purposes. Okay. Second question, can such ISP grow under the company? Oh, okay. So this is another interesting question. This will be more like going at how the ISP run their business. Okay, an ISP, if they provide very good services, then it will be easier to expand. But it depends also on how much they charge their customers as well. Okay, so I think question 2 is more, okay, is there like a best business strategy for an ISP to expand? And of course, if one comes up with a business plan that expands better, you can imagine, right? The competing ISP will also come up with something. And so the ISPs would definitely compete. I don't know about you guys. Usually what I see is that the companies with the higher amount of capital would win in the short term. Okay, but we don't know in a long term though. Okay, it really depends on the dynamics. Okay, one can potentially build an ISP with lower costs but higher performance. So that way, maybe that ISP with smaller capital can still survive and look for opportunities to grow. So question 2 there is a very good one, but it's going more towards business, and there could be multiple factors involved. Okay, and guys, so feel free to use either platform Discord or live chat to ask questions. And guys, sorry for the audio of the previous 2 videos. Yeah, so this is the first time I get feedback. Thank you very much. Okay, so that way I realize also that it's better to raise the volume of those 2 videos. But the later videos should be okay. And if they are still lower, just let me know. Okay. And now we exit core and move on to the next topics. We're going to talk about the performance. Okay. And we'll start by talking about the metrics people use to evaluate the performance. And one of the major criteria in order for an ISP to expand is, of course, they offer good performance service. Okay, so here's the introductory video of the metrics. We'll be talking about 3, but this video introduces more. 2 major metrics we use, delay and loss. Where do they come from? Starting from here, we'll focus our discussion mainly on the packet-switched internet. And 1.4 is to talk about the important metrics we care about designing protocols for it. That includes delay, loss, and something called throughput, which we'll talk about at the very end of 1.4. How do loss and delay occur? Well, let me draw your attention to the example below, that'll be easier. first kind of delay is happening here in the packet that is going out, being transmitted out. That delay the packet is experiencing is called the transmission delay. That is the time it takes to transmit the packet, and we know how to calculate, don't we? It's packet size divided by the link rate. But there's a second kind of delay experienced by packets here before they get to go out. These are what packets waiting in a queue, waiting for its turn. And how can there be packets waiting in a queue? It actually happens quite often when the incoming rate exceeds the outgoing rate. So you see in the example, A and B sending packets actively together into the router. In case the aggregated arrival rate is higher than the outgoing rate here, then you will see there will be always packet here waiting to be transmitted, and therefore subsequent packets will need to wait up. And that is queuing delay these packets are experiencing. Now the calculation of queuing delay is a lot more challenging than the transmission delay. It really depends on the arrival pattern before a packet comes into the queue. Okay, now if that pattern is reoccurring, predictable, then it will be easier to calculate this. Otherwise, very challenging. Now, that explains packet delays, where they might occur. Packet might get lost as well at the router, and it happens here. Focus on this thing here. It's the packet queue. The size of the packet queue is limited. Okay. By the way, that packet queue is also often referred to as the buffer. Okay, and the buffer space is limited, just like the memory space is limited. The buffer space is just a way of calling the memory reserved, okay, to store these packets. Now, given that the amount is limited, in case congestion persists for a long time, then eventually you run into the situation. There's no longer free buffer space in the queue. In that case, arriving packets will get dropped, and therefore we see packet losses. All right, and now we focus on talking about this metric called delay. Okay, so a delay happens typically in a router, right? When packet arrives, we store the packet, and there needs to be some processing. For example, you just saw in the video that, hey, in case the next link is busy, that packet might need to get in the queue. Okay, so we look up where the destination is and find the link. But if the link is busy, we'd put the packet there in the queue. So there's all kinds of delay: processing delay, lookup delay, queuing delay. Okay, so delay in one hop, there are 4 components. Okay, so that is explained by this next video. Now, packet delay. There are 4 components. The first component is the nodal processing delay, but we just call it processing delay. It occurs right here when the packet arrives at the router. Router here checks the bit errors in case there's any, and decides quickly which output link the packet should go out. Next, queuing delay. That's the time the packet waits until it's turn to go out on the output link. So it occurs right here at the buffer space where packet queued up. But the amount of wait depends on the congestion level of the router. Component 3 is the transmission delay, and it's calculated this way: R being the link bandwidth, L being the packet length, and the time to transmit the packet out will be L divided by R. And it's happening right here at the interface between the router and the link. Final component, propagation delay. Provided the length of the physical link and the propagation speed of signals traveling the physical link, we know that the propagation delay is D divided by S. So essentially, the time for the packet to traverse the physical link. Be careful. S here is the distance the signal can travel per second. R here is the number of bits the transmitter can push out per second. Although I call S the propagation speed, R the link speed sometime, but there are 2 very different quantities. All right, now that's exercise calculating the nodal delay. So Polly mentioned that there's processing delay, queuing delay already. There's also propagation delay. That is the time it takes for the packet to reach the next hop. And at the next hop, there'll be another nodal delay one needs to calculate. Okay? So next is, let's go over 2 examples and see how one calculates a nodal delay. Now let's go through a couple examples to exercise calculating transmission delay and propagation delay. What you're seeing here is a caravan of 10 cars. Now the way to think of this scenario is this. Think of cars being bits and caravans being a packet. So we have a packet containing 10 bits in a sense. The cars will be propagating at the speed of 100 kilometers per hour over 100 kilometers, reaching the second boost. Toll booth number 1 here takes 12 seconds to service the car. All right. Question here is asking how long until the packet is lined up before the second router. All right, so transmission speed, transmission delay plus the propagation delay. So what is the transmission delay? We have 12 seconds serving per bit, and then there are 10 bits. So the time to push the entire caravan out of the toll booth is 2 minutes. And then the propagation delay is for the car to travel 100 kilometers. So 100 kilometers dividing the propagation speed. So we have 60 minutes here. And so altogether, 62 minutes before the entire caravan to reach the second toll booth. So you see, in this case, transmission speed very fast, propagation speed slow. In the second example, the configuration is slightly different, mainly propagation speed and transmission speed. Propagation speed now goes really fast, but transmission speed much slower. So question here is asking, will the first car arrive at the second toll booth before all the cars are being serviced? Let's see, when will the first car arrive at the second toll booth? So transmission delay, 1 minute. Propagation delay, so we have 100 kilometers, but we're traveling 1,000 kilometers, so we'll be spending 1/10 of an hour propagating, and that's 6 minutes. Together, 7 minutes. So the first car will spend 7 minutes before arriving at the second toll booth. Now, 7 minutes is also the time to service 7 cars for the first toll booth. That means we have 3 cars that are still behind at the first toll booth. So yes, okay. When the first bit arrives at the next router, there could still be bits not yet transmitted out from the previous router. So in this case, where the propagation speed is really fast, transmission rate very low, you had this weird situation. All right. Now, next is to explain or talk a little bit more about the queuing delay, because we see that you know how to calculate propagation delay. You know the how to calculate transmission delay. The formula is clear. But what about queuing delay? Good. Let's sum up packet delay. So there are 4 components: processing delay, queuing delay, transmission delay, and propagation delay. Transmission delay, very low, typically microseconds. We just ignore the processing delay when we calculate packet delay. Transmission delay, propagation delay, very easy to calculate. L divided by R, this quantity is often significant and especially the case for low speed links. Propagation delay, slightly harder. It varies quite a bit from microseconds to hundreds of milliseconds. So this extreme is for satellite links, for example. We've seen earlier, it could go up to 200 or even more milliseconds. Sometimes the transatlantic or trans-Pacific links, very long optic fibers, could also take up to 100 milliseconds. Now, in the process of calculating packet delay, the hardest component is this, queuing delay. Now, it's very hard to calculate accurately because it depends on the congestion level at the router. Just to give you a sip of how hard it is, let's define again, R being the link bandwidth, L being the packet size. Let's add one more variable, the average arrival rate. So L multiply A is the average bit arrival rate. That is also the incoming traffic rate. R is the outgoing traffic rate. So we could define traffic intensity being LA divided by R. So when that quantity is close to 0, that means incoming rate very low, outgoing rate very high. then no bits really need to wait. So queuing delay very small. And it's depicted here. When LA divided by R is very small, queuing delay also very small. The other extreme is here. When the intensity is greater than 1, that means there are more bits coming in than more bits going out. And when time goes on and on and on, the newly arrival bits will need to wait longer and longer and longer. And it's pretty much here, approaching infinity. Now, when the intensity is between very small to 1, delay is simply growing. And as we will be approaching infinity, you see that the curve grows quickly like that, okay, close to an exponential trend. So hard to estimate queuing delay. In fact, it takes a whole semester for a professor to teach about how one calculates queuing delay. And at the graduate school, there's advanced queuing delay that one can also take to make sure that you do a better job, okay, estimating queuing delay for highly dynamic incoming traffic. All right. So that was queuing delay that's complicated. So very often in the exams or in the assignments we will run into, we won't be challenging you calculating the queuing delay. Okay, but we'll definitely challenge you calculating the propagation delay and transmission delay. Okay, now the last video about delay. So what we will do is to show you a demo, okay, of how one measure the internet delay. Okay, so in this video, it's a little bit long, almost 5 minutes. So you will see that there's this program called traceroute. One can actually call on a Unix system. I think the same on Mac OS or on Windows, it might be called a little bit differently. So if you type that command, it's going to do something and tell you the delay going from the source to the next hub, in yet the next hub, and all the way. Okay, so traceroute. So let me explain the theory, give you an example presented by the textbook. But Polly is going to do a demo also live there in the video. Okay, pay attention to the live demo. You will see that the delay come out in a very strange way, and the output of traceroute can be complex. Okay. All right. So that was the theory part of the packet delay. One can also find out what is the real internet packet delay by trying out this program, traceroute. Okay. What it does is to measure delay from a source, one hop at a time, all the way to a destination. So this is what I'm drawing here, source to destination, and it's sending 3 packets, one at a time, to reach each of the routers along the way. So router there receiving such a packet would return by sending a reply back to the sender. Now the sender there can time the interval between the transmission and receiving the reply and gets one estimation of the round trip time between the sender to the router. So it works like this. 3 probes to the first router, 3 round trip time estimation. 3 probes to the second router, 3 round trip time estimations to the second router. And this goes on and on until it reaches the final destination, and then the traceroute program stops. The output of the program looks like this. This is an example. Trace routing from Gaia, UMass.edu to Oricom France. So this is saying first hop router's name is CS-GW at IP address 128.something.something.something. And there are 3 round trip time estimations, 1 and 2 milliseconds respectively. What's a little bit interesting is between hop 7 and 8. There, you see at hop 7, round trip time was about 22 milliseconds, but suddenly to hop 8, the delay is about 100 milliseconds. So that is the transatlantic links connecting from US to Europe. A little bit more interesting is also hop 17 and 18. You see stars. That means the routers are not responding. Okay, and it could be because the probing messages are lost or the replying messages are lost. But it's more likely that the router is turned off replying to these. Routers are on, but the routers turn off replying these probing messages. Well, let's try, sending a trace route ourselves from here. How about that? Let's go over to a terminal and then trace route to say Google. How about that? But first hop router, well, it didn't tell me the name of the router, so chances high that the router doesn't have a name. Okay, delay reasonable, 10 millisecond, 3 millisecond, and another 3 millisecond. Router 2 here, well, either the probing messages are lost or router turns off the functionality of returning to trace route probes. Now third hop, ooh, 30 milliseconds, suddenly much higher. Okay, fifth hop, delay not much higher than the third hop. And you see here, when it's star, 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 it takes longer time. It's because when the traceroute program sends the probing packet, there's a timeout interval. Traceroute will wait until the time exceeds the interval. Then it determines that, hey, the router is probably not going to respond anymore. So forget about the first probe, send the next probe. Next probe waits also some amount of time. Timeout, give up, and then sends the third probe. Okay, good. Finally, we reached www.google.com. But the name is actually quite different. TSA something something. Interesting. And the end-to-end delay, end-to-end round-trip delay to www.google.com is about 20-something milliseconds. Now, something that's very odd is here. Hop 8. If you look closer, we do have 3 round-trip time estimates. But each time, number A here along the way, the 8th hop, is slightly different. IP address is 101, 49, and 97. So you see here, packets, although going to the same destination, coming from the same source, as they go on the internet, the routes could actually change. Also, you see, hey, the time it takes to reach hop 5, 30 milliseconds, but the time it takes to reach hop 12 is only 20-something seconds. So the load of the internet changes also over time. So sometimes when you are probing to a closer router, could take a longer time because it was busier there. But when the traffic load drops and when you're probing a router that are farther away, you could get a shorter round trip delay. Yeah, very curious. And let's go back to the slide. And it turned out that it's a good time to start the next quiz. All right, so we're supposed to start quiz 6, but you know what? We have only 2 minutes left. So what I propose we do is that we'll start doing quiz 6 tomorrow morning, okay? But in the meantime, what I do is if we go to the score space, you will see already that quiz 6, yeah, the problem is already there, okay? So what you're seeing there at the top is the exact example we talked about in the video, okay? Now I'm asking you some finer grained questions and see if you can answer. So you guys can actually think about what you're going to address these between today and tomorrow morning. But tomorrow morning, we'll start by working on the quiz. Okay, and Polly will try to go over the quiz 6 definitely, okay, in more detail. And then we suggest that we use the time to address another question from the student. Okay, so this is from Alan. Okay, so, well, small question. Well, this is actually a big question, Alan. Okay, so he's asking about the trade-off between the layers of hierarchy and bandwidth. Okay, this is a very good question, and I think, Alan, you meant the layer of hierarchy versus the available bandwidth. Okay, so I mean, we can also always connect 2 routers using cables, and the amount of bandwidth allowed, okay, on the cable is, of course, the capacity of the cable. But the thing is that if you build a tree-like topology, okay, at the highest level, there's a chance that all the traffics go all the way up, and they all kind of bunch up, and you can have a lot of traffic there at the top. Okay, so that can be a lot of congestion as well. And in the excuse me, in the end, with all these many flows competing for the bandwidth, each flow then gets a small cut, okay, of the link capacity. Okay, this question, Ellen, is very related to the third metric we'll talk about tomorrow as well. It's called the throughput, because yeah, of course we can try to send data, you know, just dump it into the internet, but whether the receiver gets them or as fast as you dump the data into the internet? That is a different question. Okay? So I think you're going at the problem like that. And I guess you pay attention to the video where I show how the internet is designed, right? Of course, you can build a network that is very well connected, right? Then you find very, very short paths. The likelihood of finding really short paths, meaning small number of hubs from one point to another point, is higher. If it's more like tree, then hey, it will be less costly, okay? But then you have this issue. At the higher of the hierarchy, okay, you have many traffic, lots of traffic. Okay, so for those routers at the higher hierarchy, then you will need to have more capacity. Okay, and it's indeed costly, okay, to have that extra capacity. So you are asking a big question that the ISPs are always, okay, debating and redesigning their network about. Okay, and you are right, your intuition is right, that if you build a tree-like topology, then you don't need to purchase all that many cables, okay, that much capacity. But in the end, you will have a few routers, and you need extra high bandwidth, high capacity for those cables. Okay, so which one is cheaper? In fact, having lower capacity and let them scatter around is cheaper than the higher capacity. The cables are expensive, all right, but the most expensive are the routers who connect to these high capacity cables. You can imagine, right, with so many packets coming into a router, okay, and so many packets going out of the router, that processing there, the router needs to do, there are, tons of these packets that are being processed in a short amount of time. So that router needs to be super high end. And typically those are the most expensive network equipment around the world. Okay, and that's where the ISP spend a big part of their budget on. Okay, nowadays what I can say is that, for example, Google, who also have a big server farm and one of the biggest content service provider, they also build their content network, thinking how they can balance the load. Okay, the keyword is observe the traffic pattern and then optimize and balance the load such that you know how much capacity there are and how high speed the router needs to be. In the meantime, lowering the cost. It's an optimization problem. Okay, that's why many of these ISPs and big companies, internet companies, also hire scientists like you guys. Some of you might become to try to cut down the cost, okay, of operating a major company, okay, and sustaining the operation, smooth operation of the internet. Okay, so that is what I would like to end the lecture today. Guys, we are going a little bit slow this semester because, hey, expect we go sometimes even slower because we do have a bigger class this semester. We have 39. That is pretty much the cap of the class, and this is the record high number of students taking this course. But you see also that the way I teach might be very different from many of the professors, because we are definitely encouraged to allow more students to take a class at the time. So again, we have a capacity issue, but you see that there's going to be a lot of delay. That's going to be a lot of load for the teacher and the TA to handle. Sometimes we trade off the quality. We trade off the details we teach in the class. But no, I am the one who feel that details are important. So I would rather take it this way. Let's address the questions as much as we can. Okay, but of course, sometimes you guys will have more questions than you guys expect. Okay, but it's okay. It's okay. As you hear more, you are also growing a better sense, okay, of how the internet is really like. Okay, especially for a complex system like this. Take our time. Okay, so if you have questions, feel free to say it. And thank you for providing the feedbacks. And maybe it's also because that the previous classes are smaller. Okay, I don't have diverse enough of you guys. So some of you are sensitive and feel more active saying things and discover when they feel that, hey, this is something that is a little bit uncomfortable, then say it. This is great. Then so I will have an opportunity to try to improve. Okay, so think of it a better way. All right, good. Guys, last but not least, there's also a trade-off between time and quality. Okay, so that's linked towards the quality time, quality side. Okay, maybe there's not gonna be all that much time. At the end of the semester, I mentioned that we'll be covering protocols in the link layer, but it's okay. We won't be covering the whole link layer either. Okay, and in case you guys are really interested, when you know enough, usually it motivates you to know more. Then you can actually go on and study those sections or chapters more. Okay, later on, maybe in the summer. All right. So that's all for today. Tomorrow, 10:20. Let's start sharp, and we'll start from Quiz 6. And Quiz 6 is already on the score. Feel free to take a look. And if you have teammates, start discussion. Then maybe tomorrow morning, you guys will be able to respond really quick and giving something that's out of ordinary. All right? Good. So that's all for today. And I say goodbye. Okay? See you tomorrow. Bye. Oh, there you are.